Chemical Bonding, Intro and Ionic Bonding, lecture number 5. So we're going to start talking about moving away from individual atoms and where the electrons are held, and now we're going to start talking about interacting those electrons between two different atoms. Right? It could be two of the same or two completely different ones. So in order to do this, we're going to talk about moving those electrons around, and we'll see that there are 3 different ways of bonding these. The first one we're going to talk about today, this ionic bonding. We've talked about ionic bonding before, but let's revisit it in terms of electrons in this case. In order to talk about this ionic bonding, let's first talk about another way we can display these electrons. Now, instead of talking about all of the electrons like in the electron configuration, we're only interested in those that are available or have the ability to form bonds. And those are those valence electrons. So we've come up with this shorthand to show those valence electrons, and that's called the Lewis electron dot symbol. So we're taking that elemental symbol and now we're showing some pictorial representation of where those electrons are, or how many electrons are available. So it's this pictorial representation. So in order to do this, we're going to take our chemical symbol. So down here, in this case, we have nitrogen. And we're going to determine the number of valence electrons that are present. Nitrogen, because of where it is, has 5 valence electrons. Right? It's the 2s, 2, and then the 2p, 3. 5 total. So we're going to put that elemental symbol, nitrogen, and then around there, one at a time, we're going to put a dot representing those electrons. So we're going to go around all 4 sides of this sort of square represented by this elemental symbol, one dot at a time. So just like when we did the electron configuration, we'll completely or half fill each place, put one dot on each 4 sides before we go back and pair. Right, so the number of dots is going to represent the Lewis dot diagram. So here you can see, and it doesn't matter how we arrange these 5 electrons around it, as long as we have only one set of paired. Right, so if we think about the Lewis electron dot symbol for hydrogen, it would be the H with 1 dot. Right? But it wouldn't matter which of those 4 sides we put that on. Helium would be He with 2 dots. Carbon would be the C, and it has 4 valence electrons, so there would be 4 dots, 1 around each side, representing there's 4 electrons. So these electrons really are indicative of which electrons are available to do bonding. Right? So for a metal, the total number of dots in the Lewis symbol is going to be the number of electrons that atom loses when it forms a cation. Right? So if we think about sodium, it's going to have 1 dot. When it forms a cation, it's going to be losing that dot. Right? Magnesium is going to have 2 dots. It loses 2 electrons. For a nonmetal, it's going to be the number of unpaired dots equals the number of electrons that it's going to gain when it forms the anion. So if we look again at nitrogen, there was 3 unpaired dots, 3 unpaired electrons. It can gain 3 electrons to form the 3 minus. If we look at fluorine, it's only going to have 1 unpaired dot, so it needs to gain 1 electron. And this leads us to what we call the octet rule, that states when an atom bonds, they lose or gain electrons or share electrons until they get this filled outer level of 8. I always think of this as more of a guiding principle, because we'll see later that we violate this rule almost as much as we follow it, but it's a guiding principle. All these atoms want a filled outer shell of 8 electrons, at least. Sometimes we'll do more. That's sort of our guiding principle, with the exception of the first 2, which only want 2 because of the small size. There's only that 1 orbital. Right? So our guiding principle says we always want to get 8 around this central atom. And we'll see that there's 2 main ways that we do that. The first is in this ionic bond. And an ionic bond is formed when a metal actually transfers electrons to a nonmetal and forms ions. And these ions themselves are attracted to each other through Coulomb's law to to form this ionic compound. Right? So in an ionic bond, we get a complete transfer of electrons. One atom is going to give its electron to another, right? Or multiple electrons. So the number of electrons that are lost by the metal is equal to the number of electrons gained by the non-metal atoms or atoms. So it's got to be a equal number. So if it's losing 2, the metal is losing 2, something else has to gain 2 electrons. Either one atom has to gain 2 or 2 atoms have to gain 1. Right? So we're completely transferring this. So we can show this transfer in any one of the representations we've talked about so far. Right? We can talk about it in the electron configurations. So here we have lithium. It has that 1s, 1 electron in the 2s orbital. It's going to transfer that electron into that available spot in the 2p of fluorine. Right? So it's going to go from, as it shows here, we're going to end up with fluorine having a filled outer shell. Lithium is going to lose it, so it has, again, a filled outer shell because it has that filled s. Or we can talk about it in the orbital diagrams. Right? You can see here in the red that single electron in the 2s is going to be transferred and pair up with the available spot in the 2p. Or we can do it, show it in the Lewis dot diagram, where one electron, one dot, physically moves from one atom to another to form now lithium with no dots around it and fluorine with 8 dots around it. Either way, we get this complete transfer. The electron is physically moving from one atom to another. And then those 2 ions that are formed are going to be associated with each other through this attraction of the positive charge and the negative charge. There's going to be an interaction. And that attraction, when it's in a solid form, that attraction is referred to as the lattice energy. It's going to form a crystal lattice. The way we calculate this energy, it's an enthalpy, right, is that we can primarily do it through Hess's law. Remember, Hess's law states that since enthalpy is a state function, that it doesn't matter how we do that transition, the sum of those changes in energy is going to be equal to that difference. So if we look at here, the lattice energy of lithium fluoride is going to be equal to the energy that we have of the lithium as a solid and the 1 fluorine, or 1/2 F2. We're going to take that apart and stepwise go from those 2 species into this solid combined lithium fluoride compound. So the first thing we have to do, as you can see, is you're going to take the lithium and you're going to make it a gas. So that is the heat of vaporization, delta H of vaporization. Then you're going to break apart that fluorine molecule. So you're going to break apart the 2F, which is the bond energy there, between the energy that's in that bond of those 2 fluorines. You can see that's a fairly small energy in comparison. Then we're going to ionize the lithium. Again, remember from the last chapter that this is takes energy to pull that electron out. So we're going to be higher in energy. So now we have lithium as a plus as a gas, plus fluorine atom as a gas. To get fluorine to be a minus, we have to do a electron affinity reaction. We have to add 1 to it. Remember, this is an exothermic process, so it's going to lower it in energy. So now we have the lithium plus and the fluorine minus. When those 2 come together, that is going to be our lattice energy. So we can calculate this, knowing all these other steps, or looking up all these other steps, we can calculate using Hess's law this enthalpy, this lattice energy. Right? This is referred to as the Born-Haber cycle. Right? Where we're doing this, we're taking those 2 individual atoms in their elemental form and going through the process till we form this new lattice. Right? So this is just an application of what we did last semester, but the implications for that is the periodic trends in this lattice energy. The lattice energy is defined as the energy required to separate 1 mole of this ionic species in the gas form. And it's the way we measure the strength of this ionic bond. And because this is a relationship of charges, this is directly related to Coulomb's law, which says that the attraction between two charges is a function of their charge magnitude and the distance between those. Right? So the bigger the magnitude of charges, the more they're going to attract, and the closer they are together, the stronger the attraction is going to be. Right? Therefore, this lattice energy is going to increase with atomic size. The bigger they are, the bigger the charge there's going to be affected, it doesn't increase. It's going to be affected by the size and the charge. So as the size increases, which means that two charges are being separated in space, that's going to be a smaller interaction. Right? Which means that the lattice energy is going to go down as we go down the periodic table, because the size of those ions, those individual atoms, is going to get bigger. But as the magnitude increases, that charge is going to increase. So if we have a 2 plus interacting with a 2 minus, that's going to be a stronger interaction than a 1 plus and a 1 minus. Right? So that's going to be affected by its position there. Next time we're going to talk about the other type of bonding, covalent bonding.